proceed to open channels. So this is also a famous topic in civil engineering board exam. Okay, so we are using the Manning's formula. So for pipes, we have also a Manning's formula when it comes to head losses. That is the head loss for Manning's. That is the H sub n equal to the 10.29 roughness coefficient, that is n, n squared, the length multiplied by the discharge squared. This is divided by the diameter raised to 16 over 3. That is for pipes. But when it comes to open channels or canals, we are using the velocity from chassis. So the formula for velocity from chassis is, this is the C, the square root of R, that is the hydraulic radius multiplied by the hydraulic slope. Then Manning's introduces the equivalent of C. The equivalent of C is 1 over the roughness coefficient, the hydraulic radius raised to 1 over 6. Then all we have to do is substitute this value of C from chassis formula. Then I will be having the equivalent of the velocity now as the value of C from Manning's is 1 over the roughness coefficient, hydraulic radius raised to 1 over 6. So the square root of RS is the same as RIS raised to 1/2. So we have the same base R. All we have to do is add the exponents. So we have now the velocity is now equal to 1 over the roughness coefficient. That is R. 1/6 plus 1/2 is 2/3. The hydraulic slope raised to 1/2. So this is our formula for velocity for the Manning's formula. So by the way, what is the equivalent of R? This is the hydraulic radius. For the hydraulic radius, this is equal to the cross-sectional area of the channel divided by the wetted perimeter. Okay, so if we are to compute for the discharge or rate of flow over an open channel, that is basically equal to the area multiplied by the velocity, or we can have it as the discharge area, and we are using the velocity for Manning's from Manning's is 1 over n. Hydraulic radius raised to 2 over 3, hydraulic slope raised to 1/2. Okay, so let's have some examples. Okay, so let's have this example. A rectangular channel with n or roughness coefficient equal to 0.015, 10.67 meters wide, is to carry water at a flow rate of 99.6 cubic meters per second. So that will be the discharge. We have Q is equal to 99.6 cubic meter per second. The slope of the channel is 0.0087. Determine the depth of flow. So this is our illustration. The base width is 10.67 meters and roughness coefficient, slope, discharge. We are looking for the depth of flow. So if you are to go back on our basic equation for discharge, that is, the discharge is equal to area times the velocity. We have the discharge is equal to area, then velocity by Manning's, that is 1 over n. The hydraulic radius raised to 2 over 3. The hydraulic slope raised to 1/2. So what is the equivalent of the hydraulic radius? This is the area divided by the wetted perimeter. So for a rectangular section, what is the area of this rectangular section? That is basically B times D, base width times the depth. So we have a base width of 10.67 multiplied by the depth of flow. This is divided by wetted perimeter. This is the contact surface of water and the channel. So we have, for rectangular section, basically the equivalent of our wetted perimeter. Again, if you are to write, area is basically base times D. The wetted perimeter is, that is the base width, that is B, plus depth on both sides, that is plus twice the depth. So the equivalent of the wetted perimeter, we have a width of 10.67. Okay, this is plus twice of the depth. This is plus 2D. That will be our hydraulic radius. So again, our area, the area is 10.67 meters wide times the depth of flow. Now all we have to do is substitute on this equation. So we have the discharge is given as 99.6 cubic meters per second is equal to, what is the equivalent of our area? That is equal to 10.67 meters multiplied by the depth, also is in meters, then multiplied by the velocity, that is 1 over roughness coefficient. We have 0.015. Equivalent of the hydraulic radius, we have the area, that is 10.67, multiplied by the depth. I divide by the wetted perimeter, that is the base width, 10.67 plus twice the depth. This is raised to 2 over 3. Then we have a hydraulic slope given as 0.0087. This is raised to 1/2. We are now solving for the depth of flow. So we are just to input this equation. We have 99.6. That is equal to the area, that is 10.67 multiplied by the depth, let's say alpha of x. That is multiplied by the reciprocal of the roughness coefficient, 0.015. Then multiplied by the hydraulic radius, that is the area, 10.67 of the depth. This is divided by the wetted perimeter, that is the base width, plus twice the depth. Then this is raised to 2 over 3. And then multiplied by the hydraulic slope, we have 0.00, or that is 0.0087. And this is raised to 1/2 or 0.5. Then we are using shift solve. Before pressing equals, we may assume a value near to the values of the choices. Let's say I'll be choosing 1, then equals. Just to speed up the iteration of the calculator. So we have the value of x is now equal to 1.4007. Or if I to write it on 3 decimal places, that is the same as 1.0 or 1.401 meters. So this will be our answer for problem number 12. If we are to check this value on our choices, so the closest value to 1.401 is 1.4 meters. We have letter C. So this will be our answer. We have letter C, 1.4. That will be our answer for problem number 12. And this is our solution. So let's have this example. An earth canal carries water at a depth of 1.5 meters. The canal is 6 meters wide on the bottom and has sides looped 2 horizontal, 1 vertical. Use N is equal to 0.025 and S is equal to 0.0002. Compute the discharge by Manning's formula. So these are the given and our illustration. So how do we compute for the discharge? We have discharge is equal to area times the velocity, or the area multiplied by 1 over roughness coefficient, hydraulic radius raised to 2 over 3, hydraulic slope raised to 1/2. Na? All we have to do is determine the area or the dimension of this trapezoidal channel. So we have a slope of 1 horizontal and 1 vertical, 2 horizontal. What will be the dimension of this channel, or what will be the dimension of the top base of this trapezoidal channel? So we need this value. Let's say this is B. If we are to project this distance from the bottom of the open channel, this is the same as 6. Let's say this is distance x and distance x. So using the slope, 1 vertical is 2 horizontal is equal to, our vertical is 1.5 and our horizontal is x. So basically x is equal to 3 meters. So we'll be having the top base is the bottom base plus twice of x. And that is, I will be having the value of the top base is now equal to, the bottom base is 6 plus twice of x, that is twice of 3. Then this is equal to 12. Or we have that as 12 meters. So this is equal to 12 meters. I had to compute for the area of a trapezoid. The area of a trapezoid, we have the area is equal to the average of the parallel bases, then multiplied by the depth. So our top base is 12, our bottom base is 6. This is divided by 2, and the depth of flow is 1.5. So let us compute for the area. That is 12 plus 6. This is divided by 2, then multiplied by 1.5 meters. So our area will be equal to 13.5 square meters. So the area is equal to 13.5 square meters. So that will be our area. So next thing to solve is the wetted perimeter. So again, our wetted perimeter is the lining of the channel, or that is the contact surface of water and the channel. So how do we compute for the wetted perimeter? So this is the wetted perimeter. Let's say the piece of W. So we need the dimension of this, the slope side or the sloping side of the trapezoidal channel. We can have it by Pythagorean theorem. So using this right triangle. That is x. What is the value of x? That is 3 squared plus what is its height? That is 1.5 meters. So we'll be having the value of z, or that is the dimension of the inclined side of the channel. We have that as the square root of 3 squared plus 1.5 squared. That is 3 square root of 5 over 2. We have 3 square root of 5 divided by 2. How do you compute for the wetted perimeter? The wetted perimeter is basically equal to the bottom base plus twice of the inclined sides, or the inclined side. So that is 2 times z. So we are now computing for the wetted perimeter. Our wetted perimeter is equal to the bottom base plus twice of z. This is equal to, bottom base is 6 plus, we have twice, what is the value of z? We have twice of the value of z, that is 3 square root of, what's that value again? 3 square root of 5. We have 3 square root of 5, this is divided by 2. Or we'll be having the equivalent of the wetted perimeter as 6 plus 3, the square root of 5. Okay, so how do we compute for the discharge? I think we are now ready for substitution using this equation. We are computing for the discharge. What is our area? That is area equal to 13.5. This is multiplied by 1 over, roughness coefficient is 0.025. Hydraulic radius is the area, that is 13.5 divided by the wetted perimeter. So we have that as 6 squared plus 3, the square root of 5. So this value will be raised to 2 over 3. Our hydraulic slope is 0.002. This is raised to 1/2. So all you have to do is compute for the value. So we have the area is equal to 13.5. This is multiplied by 1 over the roughness coefficient, 0.025. Multiplied by the hydraulic radius, that is the area, 13.5. divided by the wetted perimeter, we have 6 plus 3 square root of 5. So this value I raised to 2 over 3. Then I multiplied by the hydraulics loop, we have 0.0002. This is raised to 1/2 or raised to 0.5. So what will be the discharge for this trapezoidal channel? We have 7.951 cubic meters per second. Okay, so that is, we have a discharge equal to 7.951 cubic meter per second. So we check this value on our choices. Okay, the computed value is 7.951. Closest value on our choices is we have letter A, 7.95. So this is an example of a trapezoidal channel. Okay, so let's have this example for questions 14 to 16. An open channel is to be designed to carry 1.5 cubic meters per second at a slope of 0.007. The channel material has an N value of 0.012. Number 14, find the depth of flow for a most efficient rectangular section. Now, if we are talking about most efficient sections, these are sections with the least possible perimeter. So they can carry the same discharge as ordinary open channels, but I will be having least perimeter that will result to least excavation for the channel or least material to be used in the lining of the channel. So how do we determine the dimension of a most efficient section? So let's have first, for problem number 14, it is a rectangular channel. Okay, so since this is a least perimeter, we can apply minima from calculus. But since for board exam, we have a shorter approach, that is, we are to assume that most efficient sections are half of regular polygon. So for a rectangular section, we assume a half of a square. That will be the resulting most efficient rectangular section. So for example, we have a square section. We have to do is consider its half, and that will be our most efficient rectangular section. So we are just considering half of this square. Then we are to start with the depth. Okay, let's say this is the depth of the most efficient rectangular section D. Then we may erase the upper part. So if we have the depth of flow is D, basically half of its side or half of the side of the square. Therefore, we have the dimension of the base will be twice the depth. Then, what will be its resulting area? The area is equal to 2D times D, that is equal to 2D squared. What will be the resulting wetted perimeter? That is, we have D on both sides, then 2D on the base, that is the same as 4D. The hydraulic radius for the most efficient rectangular section is the area divided by the wetted perimeter. Our area is 2D squared. This is divided by, we have 4D. So we can simply conclude that the hydraulic radius for the most efficient rectangular section is simply, we have the depth over 2. Now, computing for the depth of flow for the most efficient rectangular section, this is for problem number 14. We have discharge is equal to area times the velocity. What is our discharge? The discharge given is 1.5 cubic meters per second. What is our area? So we have area is equal to, that is 2D squared. Multiplied by 1 over roughness coefficient, that is the velocity per Mannings. This is the same as area multiplied by 1 over n, hydraulic radius raised to 2 over 3, hydraulic slope raised to 1/2. So this is 1 over the roughness coefficient is 0.012. Hydraulic radius is simply equal to D over 2. This is raised to 2 over 3. Then the given slope is equal to 0.007. This is raised to 1/2. So in this equation, okay, we are now computing for the depth of flow. That is, we have 1.5. That will be equal to, the area of the most efficient section is 2 of, let's say, d squared, or 2 alpha x on our equation. Okay, multiplied by the reciprocal of the roughness coefficient, 0.012. Then multiplied by the hydraulic radius, that is simply the depth over 2. Let's say alpha x over 2. And then this is raised to 2 over 3. Then we have the hydraulic slope. That is equal to 0.007. And this is raised to 1/2 or 0.5. So we are now solving for the depth of flow for the most efficient rectangular section. And we have our value 0.515. 0.515 meter. This will be our answer for question number 14. If we are to check on our choices, that is 0.515. Closest value is 0.52 on letter A. Okay, we proceed to problem 15. Find the depth of flow for a most efficient triangular section. So if you have to recall, for the most efficient rectangular section, this is half of a square. But what about for the most efficient triangular section? So this will be the same as half of, we are using the same, half of a square for the most efficient rectangular, most efficient triangular section. So for example, we have this square, but this square will be rotated with respect to the horizontal at 45 degrees. So the rotation of this square will be 45 degrees with respect to the horizontal. Now we are now just considering half of this square. Then we are starting with the depth. Let's say this is the depth D. The depth of flow for the channel. We may now remove the upper portion of the square, the other half. So basically, the square is divided using its diagonal. This will be our most efficient triangular section. So the slope of this section will be, since the inclination is 45 degrees, the slope is 1 vertical, 1 horizontal. So if we are to determine, for example, what will be the dimension of the top base of this triangular section, 1:1 slope. So if this is D, the depth D, this is also D, this is also D. The dimension of the top base will be equal to 2D. How do we compute for the area this time? We have the area is simply 1/2 of the base times the depth. So what is the equivalent of the area? This is now equal to 1/2. Equivalent of the top base is 2D multiplied by the depth is D. So I'll be having the area of the most efficient triangular section is simply the depth squared. This is for a triangular section. How about the wetted perimeter? As you can see, our wetted perimeter is the inclined perimeter. Considering these two inclined sides of this triangular channel. Let's say the dimension of the inclined side is Z. We are just considering this triangle. For example, we have the height or the depth of the channel is D. Then half of the triangle is also D. What is the value of Z? So this is Z by Pythagorean theorem is equal to the square root of the D squared plus the D squared. So we have the equivalent of Z is simply equal to, that is the square root of 2 multiplied by the D. So how do we compute for the wetted perimeter? Its wetted perimeter is simply equal to twice of Z. As you can see on our figure, we have two sloping sides. So the equivalent of the wetted perimeter now, the equivalent of the wetted perimeter is twice of the square root of 2, okay, multiplied by the depth. Or simply, we have 2 the square root of 2 of the depth. This is our wetted perimeter. Now for the hydraulic radius, we have the hydraulic radius is equal to area divided by the wetted perimeter. So we have the hydraulic radius for the most efficient triangular section is, our area is simply d squared. Okay, our wetted perimeter is 2 the square root of 2 multiplied by d. So cancelling one of the d, so let's say this is d, then we are to rationalize. Okay, the equivalent of the hydraulic radius for the most efficient triangular section is now simply equal to, this is the square root of 2 over 4 multiplied by the depth of flow. So these are the properties for the most efficient triangular section. Now computing for the depth of flow, we have discharge is equal to area times velocity, or the area multiplied by 1 over the roughness coefficient, hydraulic radius raised to 2 over 3, hydraulic slope raised to 1/2. Okay, what is the given discharge? The given discharge is 1.5 cubic meters per second. What is our area? The area is simply equal to d squared. 1 over roughness coefficient is 0.012. Our hydraulic radius is the square root of 2 over 4 multiplied by the depth of flow. This is raised to 2 over 3. The given hydraulic slope is 0.007 and this is raised to 1/2. So we are now computing for the depth of flow for the most efficient triangular section. This is 1.5 equal to, we have 1.5 is equal to our area, that is the same as the alpha x. We have alpha x squared, okay, multiplied by the velocity, that is 1 over our roughness coefficient, 0.012, then multiplied by the hydraulic radius. Okay, our hydraulic radius is the square root of 2, okay, over 4, then multiplied by the depth. Let's say this is alpha. Okay, we have alpha x. And then this is raised to 2 over 3. Then multiplied by the hydraulic slope, we have 0.007. And this is raised to 0.5 or 1/2. Then shift solve. Okay, we have the depth of flow is now equal to 0.72888, or we can have it as 0.729 meter. If we are to check this value in our choices, for number 15, the computed value is 0.729. In our choices, the closest value is 0.73. That is letter, we have letter C. We proceed to question number 16. Find the depth of flow for a most efficient trapezoidal section. For the most efficient trapezoidal section, we are to consider a half of a regular hexagon. Half of a regular hexagon will give us the dimension for the most efficient trapezoidal section. So from this hexagon, we are just considering again the half of this shape. Okay, that will give us the most efficient trapezoidal section. Then we can erase the upper portion. Then again, we are starting with the depth. Let's say this is the depth d. So automatically the inclination of this side will be 60 degrees. One advantage for the most efficient trapezoidal section, if we are to divide the area into triangles, the resulting triangles will be equilateral triangles. That makes, for example, we are to determine the value of the base. The value of the base or lower base and the value of the top base will be, okay, the value of the top base will be equal to twice of the lower base. And one thing more, the value of the lower base will be equal to the dimension of the sloping sides. Since, again, we have equilateral triangles. All sides are equal. So, the value of the bottom base is the same as the sides or the inclined sides. So, how do we compute for the value of the inclined side? We are considering the triangle on the side. So, we have a height of D. The inclination, or this angle is 60 degrees. This is the sloping side. Okay, we can use the function of sine. Sine of 60 degrees is equal to D divided by the hypotenuse is Z. The value of Z, or the same as the value of the bottom base, will be equal to the D divided by sine of 60 degrees. Okay, so what will be the equivalent of the value of Z or the value of B? That is the same as, we have 1 divided by, what is 1 over sine 60? So we have, that is 2 square root of 3 over 3. So this is 2 square root of 3 over 3 of the depth. That will be the value of Z or the value of B. Okay, how do we compute for the area? So computing for the area of a trapezoid is the average of the parallel bases, multiplied by the depth. We have the area. What is our top base? That is 2B. But what's the value or equivalent of B? That is 2 square root of 3 over 3 of the depth. Okay, then plus the lower base is the same as 2 the square root of 3 over 3 of the depth. This is all over 2 multiplied by the depth. So we have the area, the area of the most efficient trapezoidal section. If computing for that value, this is 2 times 2, we have 4. Plus 2 is 6 divided by 3 is 2 over 2. So that will give us square root of 3. D times D, square root of 3, D squared. This is the area of the most efficient trapezoidal section. What will be the equivalent of the wetted perimeter? So the wetted perimeter, as you can see, since we have the value of Z is equal to the value of B, and that is equal to 2 square root of 3 over 3. We have the value of the wetted perimeter is the same as 3 times Z, or the same as 3 times B. So we'll be having the value of the wetted perimeter is 3. The value of B or the value of Z is 2 the square root of 3. This is divided by 2 square root of 3 divided by 3 of the depth. So if we are to simplify the equivalent of the wetted perimeter for the most efficient trapezoidal section, that is basically 2 the square root of 3 multiplied by the depth. Then how do we compute for the hydraulic radius? Hydraulic radius is the area divided by the wetted perimeter. What is our R, or the hydraulic radius? Area is the square root of 3 multiplied by D squared. This is divided by wetted perimeter is 2 the square root of 3 of the depth. So cancelling D squared, D and D squared. So we have remaining D, also cancelling square root of 3. Basically, the equivalent of the hydraulic radius for the most efficient trapezoidal section is simply D over 2. Similar to the hydraulic radius for the most efficient rectangular section. So we are now computing for the depth of flow, for the most efficient trapezoidal section. So this is, we have the discharge is equal to area times velocity, or this is area. Velocity by Manning's is 1 over n. Hydraulic radius raised to 2 over 3. Hydraulic slope raised to 1/2. The given discharge is 1.5 cubic meters per second. Area for the most efficient trapezoidal section is the square root of 3 D squared multiplied by 1 over roughness coefficient 0.012. hydraulic radius is simply d over 2. This is raised to 2 over 3. Our hydraulic slope is given as 0.007 raised to 1/2. Okay, computing for the depth of flow, this is 1.5, okay, equal to our area, that will be square root of 3, then multiplied by, okay, the depth, let's say this is alpha x, then multiplied by 1 over, okay, the roughness coefficient is 0.012, multiplied by our hydraulic radius is simply, okay, the depth over 2. On our calculator, that is alpha x over 2. Okay, then is this is raised to 2 over 3. Okay, then multiplied by the slope, we have 0.007. Okay, this is raised to 1/2 or 0.5. Okay, raised to 0.5. Okay, then we're doing shift solve. So we have 0.037749. Do we if we have to check that value, do we have that value in our choices? Maybe I have a wrong input on our calculator. Okay, let us check. 0.007, 2/3 of d over 2, 0.012, 1.5. Oh, sorry. So this is supposedly 1.5 of alpha x squared. Okay, that is our area. Okay, again, so a little correction on our input on our calculator. It should be 1.5 the square root of 3x squared. Okay, so we are repeating shift solve. Okay, the value will be equal to, we will be having the depth equal to 0.544 meter. Okay, that's 0.54396 or 0.544 meter. Okay, let us check this value in our choices. So 0.544, the closest value in our choices for question number 16 is also letter C, 0.54. So this will be our solution for the most efficient sections. Okay, so we proceed to orifice. So we are to discuss or study the behavior of fluid or liquid coming out from an orifice or small holes. So for example, we have this orifice. If we are to observe what will happen to the liquid as it passes through the orifice, basically, the liquid will be contracted. So, since it is contracted, it will not occupy or it will not fully occupy the area or the area of the orifice. So, this contracted area is called or also known as it is called the vena contracta, the contracted area. Since we have a contracted liquid coming out from an orifice, how do we compute for the correct values like the discharge or the velocities? So basically, if we are to, for example, determine the velocity of flow coming out from an orifice, that is from potential energy to kinetic energy. So what is the equivalent of potential energy? That is the mass acceleration due to gravity times the head, or this is the height of the liquid directly above the orifice, considering the surface of the liquid is zero pressure. Then for kinetic energy, this is 1/2 the mass velocity squared. So we are to cancel the mass. If we are to compute for the equivalent of the velocity of flow, the velocity will be equal to this the square root of 2gh. But basically, this formula is purely theoretical. Theoretical for a reason that we are not considering some factors like the contracted area or the vena contracta. So through laboratory experiments, we can perform to determine the coefficients. So the coefficients can be determined using, or if you are to follow a laboratory experiments for the coefficients of for orifice. So we have the first coefficient. This is for the velocity. Let's say the coefficient of velocity Okay, for the coefficient of velocity, that is the c sub b equal to, this is equal to the actual velocity divided by the theoretical velocity. Then when it comes to discharge, or that is the Q, or the flow rate, when it comes to discharge, we have the coefficient of discharge. This is equal to the actual discharge divided by the theoretical discharge. Then lastly, we have, this is the coefficient of contraction. This is for the vena contracta. Okay, for the coefficient of contraction, that is the C sub C, that is equal to the area of actual, which is, this is the area of the vena contracta, then divided by our area theoretical. Basically, this is the area of the orifice. Okay, so these are the coefficients that can be determined using a laboratory experiment. So for example, how do we compute for the actual velocity? So therefore, actual velocity is equal to the c sub b multiplied by the theoretical velocity. So what is the equivalent of the theoretical velocity, or what is the equivalent of our actual velocity? That is now c sub b multiplied by theoretical velocity is the square root of 2gh. Then, for example, how do we compute for flow rate actual, or the actual flow rate? That's equal to c sub d multiplied by the theoretical discharge. Okay, this is the same as we have c sub d, then multiplied by, how do we compute for discharge? That is the area times the theoretical velocity, or the area of the orifice multiplied by the theoretical velocity. Now, if we are to recall our concept for discharge, discharge is equal to area times velocity. What is the equivalent of this? What is our coefficient for discharge? Our coefficient of discharge is c sub d. When it comes to area, the coefficient is the coefficient of contraction. Then when it comes to velocity, the coefficient is the coefficient of velocity. So this will be the relation for, coefficients. Okay, so let's have an example. This is question number 17. A circular orifice 5 meters below the water surface. A circular orifice is located 5 meters below the water surface. If the tank is large and the diameter of the orifice is 5 mm, calculate the discharge if the coefficient of discharge is 0.6. So, for example, we have a tank. Okay, so let's say we have an orifice. Okay, so we have, let's say, the diameter of the orifice given. Okay, the diameter of the orifice is equal to, we have that as 5 millimeters. The coefficient of discharge is equal to, we have this is 0.6. And the head, let's say the height of water above the orifice, that will be the head of the orifice, equal to 5 meters. So we are looking for the discharge. So since we have a coefficient of discharge, we are looking for the actual discharge. Actual discharge is equal to the coefficient of discharge multiplied by the theoretical discharge. Computing for the actual discharge, this is equal to c sub d. How do we compute for discharge? That is area, but this time area of the orifice multiplied by the theoretical velocity. Our flow rate actual is the coefficient of discharge, area of the orifice. Theoretical velocity is the square root of 2gh. So all we have to do is now we are to substitute. Okay, we have the actual discharge. Our c sub d is 0.6. This is multiplied by area of the orifice, 5 mm. That is the same as 0.005 squared pi This is divided by 4 in terms of a meter. So this will be square meter. Then the square root of twice of 9.81. Then the height or the head above the orifice is given as 5 meters. So we'll be having an actual discharge equal to, let's see, sub d 0.6. The area of the orifice in terms of meter, we have 5 mm or 0.005 meter squared. This is multiplied by pi. Okay, in terms of the diameter, so divided by 4. Then this is multiplied by, we have the square root. The square root of 2 times 9.81. Okay, the head is 5 meters. Okay, then this is equal to 1.16685. Like 1.6685 times 10 raised to negative 4. 1.6685 times 10 raised to negative 4. This is in terms of cubic meter per second. If we are to check that on our choices, so all values are in liters per second. So all we have to do is convert this one. This is multiplied by, we have 1,000 liters is 1 cubic meter. So basically this value in our calculator, we are to multiply this one to 1,000 to be in liters. So we have 0.116, or we can have the flow rate actual as 0.117. This is now in terms of the liters per second. Okay, if we are to check that on our choices, 0.117, that will be, we have a letter A. Okay, so let's have this example for orifice. A tank which is 1 meter square in cross-section is filled with 3 meters of oil with a specific gravity of 0.8. If a standard 80 mm diameter orifice is open at the bottom with C, or that is the same as the C sub D, the coefficient of discharge is equal to 0.6, how long will it take to lower the liquid surface by 2 meters? So this is the case for orifice. This is the falling head. We are considering that the liquid surface will go down. How do we compute for? How do we compute for the time? Okay, so we have a formula for this one. This is the time is equal to, this is negative twice area divided by, we have C, or that's the C sub D, area of the orifice. This is the square root of 2G multiplied by, this is the square root of the final head minus the square root of the initial head. So what is the initial head of the orifice? If we say initial head, that is the height of the liquid surface from the orifice. So from our figure, our initial head is equal to, according to the problem, that will be 3 meters. So h sub 1 is equal to 3 meters. What will be our final head? If according to the problem, how long will it take to lower the liquid by 2 meters? So if the liquid will go down by 2 meters, this will be our final head, or the final height of the oil above the orifice. So our h sub 2 is, that is the same as 3 minus 2. Then our final head, h sub 2, should be equal to 1 meter. Our h sub 2 is equal to 1 meter. Now if we are to substitute for the time, so by the way, this area is the cross-sectional area of the tank. So we have the time is equal to negative 2. What is the cross-sectional area of the tank? It is a square tank with a dimension of 1 meter. So this is the same as 1 squared. I divide by coefficient of discharge. This is 0.6. Multiplied by the area of the orifice, 80 mm, or the same as 0.08 squared pi divided by 4. In terms of meter, the area of the orifice in terms of meter. Then multiplied by, this is the square root of twice of 9.81 meters per second. Then multiplied by the square root of, what is our final head? That is 1 meter minus the square root of the initial head. This is 3 meters. Okay, computing for the time. We have the equivalent of the time. Yes. This is, we have negative 2 multiplied by the area of the tank, that is a square tank, 1 meter in their dimension. This is divided by coefficient of discharge is 0.6. The diameter is 80 mm or 0.08 square meter, 0.08 meter. So squared, shift pi over 4. Then multiplied by, this is the square root of 2g, or that is twice of 9.81. Then multiplied by, this is the square root of the final head is 1, then minus the square root of the initial head, which is, we have 3 meters. Then we'll be having the value. This is 109.597 seconds. 109.597 seconds. So let us check this value in our choices. The closest value is, for letter D, we have that as 109 point. That's 109.6. Okay, so we have number 18, 109.6. So this will be our solution.